Hey everyone! I hope you're all surviving the quarantine. Today we're going to talk a little bit more about ionic compounds, and then we're going to talk about how to name ionic compounds. So first, let's start with how to calculate the molar mass or the weight of an ionic compound. So formulas for ionic compounds represent only the simplest combining ratio of the ions in the compounds, not the precise numbers of atoms of each element found in a crystal lattice. So remember last time we said that sodium chloride, or table salt, its chemical formula is NaCl. But in actuality, if we could zoom in on a crystal of salt, there would be multiple sodium ions and multiple chloride ions. We just list the simple whole ratio between them. So down below, there's actually a picture showing that we have alternating ions in our structure, but everything exists in a 1-to-1 ratio, at least for sodium chloride. Now, formula weight is the sum of the atomic weights of the atoms shown in the formula. So this is similar to calculating molecular weight. And remember, 1 mole of an ionic compound contains Avogadro's number of the simplest combining ratio of ions in the compounds. So for instance, if we have 1 mole of sodium chloride, that means we have 6.022 times 10 to the 23rd compounds of sodium fluoride. And actually, the term we tend to use here for ionic compounds is formula units. So I'm going to write that in here. So for instance, up above we wrote NaCl for sodium chloride, and that would be a formula unit of sodium chloride. So even though we have this really large crystal structure of alternating sodium and chloride ions, when we narrow down the ratio between ions, that's our formula unit. Now we can also figure out the mass of one of these formula units. So for sodium, we just have 1 for our simple ratio, and the average mass is 22.99, and we can look that up on the periodic table. And then for chlorine, we also just have 1, since there's a 1-to-1 ratio. And the average atomic mass for chlorine is 35.45. So if we add those together, we find that the formula mass for sodium chloride is 58.44. Now we can either use atomic mass units for this value, or remember that 1 U, or atomic mass unit, is equal to 1 gram per mole. So we could also use grams per mole. Now what this also tells us is that 1 mole of sodium chloride weighs 58.44 grams. And now we could use any of those equalities that we just wrote out to solve for different problems. So we could convert those into conversion factors. So let's practice calculating ionic compound mass. And in particular, these different ionic compounds contain polyatomic ions. Remember that polyatomic ions contain multiple elements with an overall charge. So we're going to try to figure out the masses if we have multiple polyatomic ions present in an ionic compound. But first, let's calculate the molar mass of KClO3. We're going to probably need our periodic table, so if you want to pull that up. I also have one on the next slide, so we'll keep referring to this as well. So for KClO3, we have potassium, chlorine, and 3 oxygens. So those are the 3 masses that we need. So let's go back and write all of those masses down. So we have 1 potassium, and we'll multiply that by its mass, which was 39.60. And instead of atomic mass units, I'm going to use grams per mole as my unit. So we're calculating the molar mass. And then for chlorine, we also just have 1 chlorine, and its mass is 35.45 grams per mole. And then we have 3 oxygens. So I'm going to multiply the mass of oxygen by 3. And the mass of oxygen is 16 grams per mole. Okay, so then I'm going to plug this into my calculator. And remember to use parentheses wherever you can. Otherwise, your calculator might assume, for instance, that you're multiplying the whole thing by 16 at the end instead of just 3. And of course, you can always pause the video if you want to try this on your own first. So when I plug this into my calculator, I get an answer of 122.55 grams per mole. So that would be the molar mass of this ionic compound. So what that also tells us is if we have 1 mole of KClO3, that will weigh 122.55 grams. But that also means we have 6.022 times 10 to the 23rd formula units of KClO3. So remember that KClO3, we have potassium and ClO3 minus. So that's our chlorate ion, our polyatomic ion. Now, the next question asks us to calculate the molar mass of calcium bonded to 2 chlorate ions. All right, so if we go to our periodic table, instead of potassium, now we have calcium bonded to ClO3 minus. All right, so let's write down these masses, and I'll use a different color here so we can keep track. All right, so we have 1 calcium, and its mass is 40.08 grams per mole. Now, how do we determine how many chlorines and oxygens we have? We have 2 of these chlorate ions. So what I'm going to do is multiply each of the elements in the parentheses by 2. So that means that we have 2 chlorines, and they both weigh 35.45 grams per mole. And then we also have 6 oxygens. So if chlorate has 3 oxygens and we have 2 chlorate ions, that means we have a total of 6 oxygens. And we said the mass was 16 grams per mole. All right, so again, we're going to plug this into our calculator and use as many parentheses as possible so we don't confuse our calculator. And the answer I got here was 206.98 grams per mole. Now, the other thing I want to bring up are significant figures. So when you're calculating the molar mass, we're usually adding things together, right? So we're going to care more about the decimal places when we're performing addition. So all of our molar masses here have 2 decimal places. So 40.08, 35.45, and 16.00. So that means our final answer should also have 2 decimal places. Now, it does depend on the periodic table you're using. Some periodic tables will give you like 4 decimal places. So it kind of depends on what values you're given. So in terms of molar masses, I'm usually not too picky about sig figs, but just something to keep in mind. All right, so last but not least, we're going to calculate the molar mass of calcium bonded to phosphate. So here we have a calcium, or 3 calcium ions, and those are bonded to 2 phosphate ions, which has a 3- charge. And I'm going to change colors again. So if we go to our periodic table, we're still using calcium, but instead of oxygen and chlorine, we're now using phosphorus and oxygen. Okay, so let's write all of these masses and then calculate the molar mass. So this time we have 3 calcium ions, and each one has a mass of 40.08. And then we're going to do the same thing we did before with our polyatomic ion. We do have 2 polyatomic ions, so we're going to multiply each of the elements by 2. So that means we have 2 phosphorus ions, or atoms. So that will be 30.97 grams per mole, according to our periodic table. And then we have 4 oxygens times 2, so that means we have 8 oxygens, and each oxygen has a mass of 16 grams per mole. So now we're going to plug this into our calculator, and the answer that I got is 310.18 grams per mole. Okay, so hopefully that helps a little bit with calculating masses for these ionic compounds. So again, it is really similar to calculating molecular weights, but if you have multiple polyatomic ions, you do want to multiply each of the elements within that polyatomic ion by the subscript. Okay. So now let's talk about how to name ionic compounds. And we'll start with binary ionic compounds. So binary ionic compounds are named using the following pattern. So we're going to start with the metal name, and then we'll leave a space. And then we're going to use what's called the stem or base of the non-metal name plus IDE. So you might remember me calling sodium chloride sodium chloride instead of chlorine. And the reason for that is we kind of chop off the end of the non-metal name and just add IDE to the end. So down below we have a chart of stem names for different nonmetals. So for instance, again, chlorine has the stem name chlor when it's an ion, and then we add IDE to the end, so it becomes chloride. And we can do the same thing to these other nonmetals. So bromine becomes bromide when it's an ion. Fluorine becomes fluoride. Oh, fluoride. And that's actually what's used to protect your teeth. Iodine becomes iodide. Nitrogen becomes nitride. Oxygen is oxide. Phosphorus is phosphide. And sulfur is sulfide. So these are all of the ion names for nonmetals. Now there's a few others that we didn't cover, but these are kind of the more common ones that you'll come across. So again, NaCl would be called sodium because we just named the metal as is, followed by chloride. All right, so let's do some more example problems here. So the first example is K2O. So we have potassium and oxygen. So again, we're just going to start with the metal name, which is potassium. Easy enough. Then we're going to leave a space and add on the name of oxygen as an ion, which we just saw was oxide. So if you do want to pause the video and try this problem on your own first, feel free, and then you can restart the video and we'll go over the other problems together. Okay, so for our next example, we have magnesium and nitrogen as ions. So we're going to start by naming the metal ion, which is just magnesium. And then nitrogen, we said, will become nitride when it's an ion. All right, and then the next example, we have beryllium and sulfur as ions. So for this one, we're just going to name beryllium as usual, followed by sulfide. And then in the last problem, we have aluminum and bromine as ions. So we're going to start by just naming aluminum as is, followed by bromide. So really not too bad as long as you can remember those non-metal ion names. And then here's a solution slide as well if you need that later. Now, there are some metals that can have multiple charges, and that can complicate the way that we name binary ionic compounds. Now, so far we've just been dealing with metals that have the same charge no matter what. But some metals, again, those of transition and intertransition elements, form more than one type of charged ion. As an example, iron can have a 2+ charge or a 3+ charge. It just kind of depends on what it's bonding to and how many electrons it's going to give up in order to form that bond. Now again, this is really only for transition metals. There are a couple of exceptions, but for this class, don't worry about those too much. So the binary compounds that contain ions, like these, are named following the pattern given earlier with one addition. The number of positive charges on the metal ion is indicated by a Roman numeral in parentheses following the metal name. So down below we have a couple of examples where iron is bonded to chlorine, but we have different ratios of iron and chlorine. So in the left-hand compound, we have this kind of powdery greenish yellow substance. And there's 1 iron and 2 chlorides. Now, chlorine is a nonmetal that always has the same charge when it's an ion. So remember, chlorine has 7 valence electrons because it's in group 7A. So it wants to gain 1 more electron in order to have 8 electrons, and that's going to give it a -1 charge. So if we have 2 negative charges, that means iron has to have a positive charge that balances those 2 negative charges. So that tells us that iron has a 2+ charge to balance out the 2 negatives. So the way that we would name this is iron, so we're just naming the metal, and then we're going to indicate its charge in parentheses and Roman numerals. So it has a charge of 2. And again, this is just to differentiate it from a very similar compound, which we'll talk about in a second. So now we need to name the nonmetal the same way we did before, so it would just be chloride. So this is iron 2 chloride. Now on the right-hand side, we have a compound that's almost kind of looks like gold, but it's not. We've got 1 iron and 3 chlorine ions. And remember, each chlorine has 1 negative charge. Now, if we have 3 negative charges, that means iron has to have a 3+ charge to balance out those 3 negative charges. So we would call this compound iron 3 chloride. And we're indicating the charge in Roman numerals and parentheses. Now, if we didn't indicate the charge on iron and we just told someone, oh, I have some iron chloride, maybe they're thinking of the green compound and we're thinking of the yellow compound. So you have to be very clear about the charge on iron, otherwise someone is going to potentially use the wrong chemical, and that could have disastrous consequences. So this periodic table shows not only the representative elements as ions, and you can see that they have predictable charges or non-variable charges, and then aluminum is also included in that. But in the middle here with the transition metals, we can have multiple charges for a few of them. So for instance, chromium can have either a 2+ or a 3+ charge. Manganese can have a 2+ or a 3+ charge. We talked about iron. And then you'll notice that there are some exceptions here. So for instance, silver, cadmium, and zinc only have 1 charge. But in general, the transition metals can have more than 1 charge. Now, you do not have to memorize those charges because you can always figure out the charge based on what it's bonded to. So don't memorize transition metal charges because, again, we can figure out their charges based on what they're bonded to. So let's name these following compounds that contain transition metals with variable charge, and I'll show you how we figure out that charge. We already went over a couple of examples, but let's go over a few more. So the first compound is Fe2O3. Now, from the previous chart, we can see that oxygen always has a -2 charge. And we have 3 oxygens, each with a -2 charge. So that gives us an overall -6 charge that's coming from the nonmetals. So we do have 2 iron ions, and in order to balance that -6 charge from the oxygens, we need an overall +6 charge from those 2 iron ions. So what we'll do is we'll divide +6 by 2, and that will tell us the individual charge on each iron. So that gives us +3. So each iron has a +3 charge. So now we know that we can name this compound iron 3 oxide. Okay, now for the second compound, we have an oxygen again, but this time we only have 1 oxygen, so it has a 2- charge. And then we have manganese, which has the symbol Mn. Now in order to balance that 2- charge, manganese has to have a 2+ charge. So this one was a little easier to figure out. So this would be called manganese 2 oxide. Oh, I forgot the E on manganese. There we go. All right, so now for the last problem. We have 1 oxygen again, which has a 2- charge. And then we have 2 copper ions. And in order to balance that 2- charge on oxygen, the overall charge from our copper ions has to be +2. So we're going to divide +2 by 2, and that will give us the charge on each individual copper. So that should give us +1. So each copper ion has a +1 charge for an overall charge of +2. So we would call this copper 1 oxide. All right, so again, you can always figure out the charge on the transition element by looking at what it's bonded to. And what it's bonded to will pretty much always have a predictable charge. And I'm not going to throw any crazy questions at you. On your quiz, I will give you questions very similar to this one. And there is the answer slide. And actually that first compound we looked at, Fe2O3 or iron 2 oxide, that's also known as rust. All right, now what if we have a polyatomic ion in our ionic compound? How do we name it? This is super easy as long as you know the names for the polyatomic ions. So the way you would name any of these types of compounds, again, you just start with the name of the metal, and then you just follow that with the name of the polyatomic anion. So that's all you have to do. So for instance, KClO3, which we saw earlier, that's just named potassium chlorate. Because again, ClO3- is called chlorate. And then if we have CaClO3 that's called calcium chlorate. And then Ca3PO4 is calcium phosphate. And remember, PO4 is called phosphate. And then in the last one, we have CaHPO4, and this is called calcium hydrogen phosphate. So HPO4 2- is hydrogen phosphate. So So again, I encourage you to go back and memorize the names of the polyatomic ions. And again, I also have flashcards posted. So next time, we're going to start talking about covalent bonds. We've been talking about ionic bonds where there's a transfer of electrons, but next time we'll talk about covalent bonds where atoms actually share electrons with each other. So I will see you in the next video.